So section 11.3 is going to discuss exponential functions. And that's a new class of function for us. We haven't dealt with these before. So let's look at those. An exponential function is going to have this form. F of x equals b to the x. That's what these functions are going to look like in general. And when we're working with those functions, I've got two examples here. Let's see, that's why this isn't zooming in for me. I got two examples. One of them is f of x is 2 to the x, and one of them is g of x equals x squared. Which one, or either, or both, or neither, is an exponential function? F of x or g of x? It'd be f of x. In order to be an exponential function, you have to have a fixed number here for the base and a variable in the exponent. So that variable in the exponent is x. Over here, this is just a regular quadratic function. This is just the graph of a parabola. Nothing new or exciting there. We're going to get acquainted with the graphs of these by plotting some points. So let's do that. I've got some points over here. We're going to do a t-table for both of our functions. First of all, when we square something, that's pretty easy. 0 squared, 1 squared, 5 squared, 10 squared. What's 20 squared? 400. Good. So nothing unusual or exciting there. 2 to the 0 power. What's 2 to the 0 power?
1.
2 to the 0 is 1. 2 to the 1 is 2. 2 to the 5. Who can do that one? Well done. 32. Now if you square that, 2 to the 10th power, 32 squared is 1,024. And the last one, let me show off here a little bit. If I square this, I'll get 1,048,576. Woohoo! Wow. Now notice that the graphs start out kind of similar, right? I mean, 1 and 0, 2 and 1, 32 and 25. They start out kind of similar in height, but after a while, what happens to the graph of the exponential function? It gets a lot bigger, a lot faster. Go ahead, Joe. What was it?
I said it gets exponentially bigger.
That's spot on, really. It gets exponentially bigger. That's exactly right. So it grows really, really quickly. And I'm going to demonstrate that in a couple different ways. But for now, let's take a look at the other side of the y-axis, that is, x values that are less than 0. Now when you square these, nothing big happens, nothing unusual. 1, 4, 9, 16, 25. But these other ones, well, nice. 2 to the negative first is 1 over 2 to the first. 2 to the negative second is 1 over 2 squared, but 2 squared is 4. And 2 to the negative third, 2 to the negative fourth. See if you can't fill in the rest of these. Figure out what they are. Nice. So this is 1 over 2 to the fourth, and 2 to the fourth is 16. And then 1 over 2 to the fifth, well, 2 to the fifth is 32. So this is interesting. What's happening to these values as I march out the x-axis towards negative infinity? So I'm marching out this way. What number are these getting closer and closer to? They're getting closer and closer to 0. In fact, you can see that on this graph over here. So on this graph, this is the graph of your exponential function. And as you move to the left of the y-axis, the graph gets closer and closer and closer to this line, to the line that y equals 0. So let me just sketch that in here. This line has a special name. It's called an asymptote. So y equals 0 is your asymptote. Talked about it today in what class? Pre-calc? Good deal. Good stuff. Now, there's actually several things that I want you to know about this graph, but let's take a look at a quick video to try and reinforce one of the features that I was explaining about this graph. And that's this one, kind of a prudential retirement video. And they actually set a world record in creating this video. So you're going to see them knock down a series of dominoes. That series of dominoes, the last one weighed 2 tons. So that's like 4,000 pounds. Yeah, that's pretty special. Yeah. So the last one's the world record. Boom. All right, so pretty cool. That's a pretty nice demonstration. But what's going on there with those dominoes is that they're getting exponentially bigger. And that's what happens ideally with your retirement money. If you're investing things consistently, then you can retire at age 63 and be out of here. See ya. Of course, who knows? We've got to hope for no more major meltdowns. In any case, let's get back to the math here. There's a couple features that I want you to know about the graph of an exponential. Assuming that b is greater than 1, one of the things is that the graph grows really quickly for x greater than 0. So the graph grows very quickly for x greater than 0. It takes off exponentially. And we say that it's an increasing graph. What else do we need to know here? In any exponential function, anything that is of the form b to the x, we can always find the y-intercept. So what's the y-intercept going to be? Well, good question. How do you find the y-intercept of a graph? Lisa? Perfect. Set x equal to 0. And I end up with b to the 0. What's b to the 0 equal? 1. Anything to the 0 power is 1. So what it's saying is that that graph is always going to pass through this point. No matter what, that point's going to be fixed on our graph, independent of the value of b. So the graph passes through 0, 1. Now, as you can well imagine, we're going to start transferring our functions around, moving around a little bit. And this is the point that I'm going to want to see the most. Where does that one get shifted to? Just like we were working with parabolas and we shifted the vertex, we kept track of where that vertex point went. This is the point that's kind of like the vertex for us here. I want you to keep track of that point most of all. Finally, there's one last feature that you can see here, and that is the graph gets close to but never quite touches the x-axis. So for x less than 0, the graph approaches the y-axis, or the x-axis, I should say. It's an asymptote. So y equals 0 is an asymptote. So those are the big things that I want you to know about the graph of an exponential. Okay, well, one other question while we're on the front side here. I've got two graphs here. Call them A and B. One of them is f of x, and one of them is g of x. Which one do you think is f of x, and which one do you think is g of x? Which one's the graph of an exponential function? Which one's the graph of the squared function? Yeah. This, I mean, take a look at what happens to this graph. It just takes off. It's really, really growing very, very quickly. Whereas this one is growing a lot slower. This is the graph of y equals x squared. This is the graph of y equals 2 to the x. Here you're seeing that exponential growth. That can be a good thing in certain situations, like if it's talking about the compound interest on your retirement money, but bad in other situations. So it depends on the application. Dallas?
Is y equals 0 an asymptote because it doesn't cross, or is it always?
It's our asymptote because the graph approaches that. Now, in some cases, you can actually cross or touch your asymptote, but quite often you're going to see functions that will approach but never touch their asymptote, and that's going to be the case with the exponential function. This will actually never quite touch 0. You can get as close as you want, but you can't touch it. All right? You're welcome. Thanks for the question. Anything else on the front side here? All right, let's go to the back side. So I started you out with the graph of f of x equals 2 to the x right here. And what I want us to do is look at shifting these things around. Let's see. So let's see what happens when we shift this around. So we've got the graph of f of x equals 2 to the x. What would happen if I looked at a different function instead? Let's say g of x equals 2 to the x minus 3. Now the important thing for us to see is that minus 3 is in the exponent. This should cause some kind of a shift in our graph. The question is, well, what's the shift? 3 down, 3 right, 3 left, 3 up. A lot of possibilities here. So what do you think? Well, let me start out by marking on this graph this point right here at 0, 1. That's the point that I want to see in our new graph. So I get this exponent. Let's see. This point comes around because I have 2 to the 0 power is 1. What would put a 0 in the exponent? What value of x would make the exponent 0? 3. So if I put a 3 in here, 3 minus 3 would be 0. 2 to the 0 would be 1. So in other words, this has a point on the graph right here at 3 and 1. So what did the minus 3 do to our graph then? Shifted it to the right. Now you may remember our work with parabolas. When we're working with parabolas, when you had a horizontal shift, that minus sign kind of looks funny because you expect something to shift to the left, but a minus is actually a shift to the right. So this one shifts to the right by 3. And what I'd like from you is for you to draw a nice graph kind of mimicking this, except going through this point at 1, 3. So I'm going to spin this around a little bit just to draw a good graph. Sorry if I'm giving you vertigo. Something like that. So that's our graph of y equals, or g of x equals 2 to the x minus 3. We got a horizontal shift to the right by 3. Let's try another graph. Is there any comments or thoughts on this one first? So let's take a look at h of x equals 2 to the x plus 2. And graph this one and see what this is going to look like. So, any predictions? What's the plus 2 in the exponent going to do to our graph? Good. Shift it to the left by 2. Start out with this point. If I shift this to the left 2, where should it be? What are the coordinates going to be? Good. Negative 2 and 1. That's the point that I want graphed most accurately. The rest of the stuff, mostly, I'll cut you some slack on. Although in this particular one, we can do a little bit more than we did with the last one. We can easily graph the Y-intercept. How do you find the Y-intercept of a graph? Set x equal to 0. So if I put in a 0 here, what am I going to get for y? Well, 0 plus 2 is 2. 2 squared is 4. All right. So 0, 4. So all right, that's kind of nice. Without too much sweat, we've got the y-intercept. And again, you're just basically going to pick up this graph and shift it over by 2. And again, at the risk of making you dizzy, let's do something like this. Let's draw our graph. There we go. So nice. So you got your g of x, you got your h of x. Both of them are just shifted versions of the graph that we dealt with. So far, so good with the shifting? Okay, good. Anything on these two that bother you so far? Anything? Let's try some other graphs. What if I was to ask you to graph, and we're going back to g of x equals 2 to the x minus 3. Is that the same thing as we just did? No. What's the subtle difference here? Well, first thing first, the difference is that the minus 3 here is not in the exponent. So you got your function 2 to the x, and then you're subtracting 3. Whereas this one, it's in the exponent. So subtle difference, but it means all the difference in the world as far as the graph is concerned. How do you think this one's going to be shifted? Down by 3. So let's start by working with this point right here. This point's at 0, 1. If I shift that down by 3, where's that new point? Good, it's at negative 2. Let me label this one while I'm at it. So that was at negative 2 and 1. This time, if it's down 3, 1, 2, 3, that puts the point here. So its coordinates are 0, negative 2. But before you start drawing your graph, keep in mind there's something else we have to concern ourselves with. Remember this line here. Bonus points. What's this line called? The asymptote. The asymptote. Good. So the equation of that asymptote was y equals 0. This line also gets shifted down by 3. So if it started out here, y equals 0, where's the new asymptote? Not quite. We're shifting it down by 3. So, yeah, it's going to be down at negative 3. So down here is where you're going to have your graph. Now I'll draw it with a dashed line because this is really not part of the graph. It's kind of a feature of the graph. It's a guide for drawing your graph, but it's not really part of your graph. So this is the line y equals negative 3. And we can use this to try and sketch in our graph. Now let me be a little bit forward thinking in my discussion of this, a lot of times people will get some points taken off of their graph by not drawing it too carefully. When this graph comes down, it gets close to, but it never touches this line. It's an asymptote. It doesn't touch that line. So you should have something that looks kind of like this. Now, if you accidentally touch it a little bit, I don't care. But here's where people run afoul of the grader. And that is, you can egregiously cross through this line, or some people are so afraid of this that they ricochet off and start going up. All right. Either one of them is bad. Just try as best you can to get close. And I'm not going to be looking at it with a magnifying glass and saying, oh, you're actually touching. No, that's not the idea. Just, yeah. Oh, at least 50. But yeah, you just want to get close here. So, hey. All right. How are we looking with that one? Okay there? Let me show you what you're going to face in Knewton. With Knewton, it's actually going to be a little bit simpler for you because you're going to deal with just a couple points. You're going to have to move some points. But one thing that might occur to you is, hey, are we always going to be graphing 2 to the x? The answer is no. You can deal with, yeah, darn, read your lips from here. You can deal with other bases. So let's look back here at this function, y equals b to the x. That's a generic exponential function. If you look at your handout, one of the things it says is that b cannot equal 1. Why not? Well, if b equals 1, it's kind of a boring function. 1 to any power is just 1. So you're just going to get a straight line. Not that fun. But if we let b get bigger, say bigger than 1, take a look at what happens. The function grows, and it has those characteristics that I showed you with an exponential function, right? There was 3 of them. Let's see if that's present in all 3 of these. So one of them was that it passes through 0, 1. And guess what? No matter how I move this around, look at that graph. It stays pinned at 0, 1. What were the other characteristics? What else was important about the graph of an exponential? At least according to your instructor. Grows quickly, yeah. Take a look at this one. Especially as we get bigger and bigger values of the base, b, that graph is really growing fast. Let's see. One more thing that was noteworthy about this. What was it? Good. Yeah. As you get to the left of the y-axis, that is, as Lisa said, for values of x that are less than 0, this graph gets close to but never quite touches the x-axis. And that's true, again, regardless of what base you're dealing with. So let me go all the way up here to b equal to 4 and look at 4 to the x. Now in our handout in just a minute, we're going to look at the graph of y equals 4 to the x minus 3. Minus 3. What's that minus 3 do to the graph? Shifts it down by 3. Let's make some predictions. We had a point at 0, 1. Where's that point going to be in our new graph? 0, negative 2. And even though it's not here, I could add it in quite easily. What's the equation of my new asymptote? Y equals negative 3. Good. And you can see that this graph gets close to, but never quite touches the line y equals negative 3. Newton's going to ask you to graph one more point. And it wants you to graph a nice integer point. It doesn't want you to graph anything really hard. So the easy thing to do would be to pick a value of x and then find the value of y. So let me go back to our handout. This graph is pretty misleading. It's not the graph of 4 to the x like we did with the other 2. That's okay. We're going to want to move all these things into place. So our the equation of our asymptote is going to be y equals negative 3. So this point has to be dragged down to here. And then your y-intercept gets dragged down to here. And finally, it's going to want you to graph one more point. And that point is going to be where x equals 1. So how am I going to find where x equals 1 with this function? I need my Jeopardy music queued up. I'll try and do it analog. Do, 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 do.
I'm just curious, so is the asymptote y equals 4 the original?
No, it's misleading. The asymptote for g of x equals 4 to the x is right here at 0. And it gets moved down 3. So yeah, it's misleading because it's not really trying to graph for you 4 to the x. It's just giving you a graph of an exponential function. It's not necessarily the one that we want. In fact, we could probably reverse engineer this to figure out what they're working with, but it's not worth our time. So your asymptotes always start out here, and then you want to shift it down. So when we shift it down 3, it's going to go through that point, y equals -3. The last thing to do is figure out, well, where is this point going to be? Oh, sorry. My bad. Thank you. So we shifted this down 3, shifted this down 3. Where's the point here going to be? Well, let's keep in mind that point has what for the x-coordinate? 1. And if I put in a 1 here, I get 4 to the 1 minus 3. 1 for x goes with 1 for y. So this point should be right here at the point 1, 1. Keep in mind my yellow line is the x-axis, not this dashed line. So you'd have to make those 3 adjustments on Newton in order to graph this correctly. Let's do some more kind of similar stuff to this. Are we okay with what Newton's going to be expecting? Yeah, but remember, the asymptote for y equals 4 to the x is going to be right here at y equals 0. And that got shifted down 3 by this one here. Anything else? Okay. Here's some other problems that are kind of similar, and again, they're coming from Newton. And what I want us to do with all these is, first of all, figure out the y-intercept. The y-intercept. And then figure out how it's been shifted. And lastly, figure out where the horizontal asymptote is. So let's start with the first one. I'll do the first one, then I'll let you do the next 3. To find the y-intercept of any graph, what do I have to do? Set x equal to 0. So let's set x equal to 0. Bianca, maybe you can help me out. That's going to give me 4 to the 0 plus 3. 4 to the 0 is, plus 3 is 4. So that's where your y-intercept should be, is at 0, 4. If you compared this graph, y equals 4 to the x plus 3 to the graph of y equals 4 to the x, how has this one been shifted from its basic graph? What's the plus 3 going to do? Up by 3. When would it be a shift to the left 3? What would have to be different about this one? Yeah, it'd have to be in the exponent. Now the horizontal asymptote is also going to get shifted up 3, so that's going to be y equals 3. Now I'll give you a little bit of a heads up on this one. We've got 3 to the x minus 2. That's going to be a horizontal shift. A horizontal shift is not going to change where the horizontal asymptote is. So the horizontal asymptote is still going to be y equals 0. There's no change in it unless you shift it up or down. So unless it's a vertical shift, it's going to be the same place. See if you can't fill in the rest of this information for these other 3 graphs. So how has it been shifted? And what are the y-intercepts? You're going to get a fraction for the y-intercept on the second of these. This one right here. It's going to be a fraction. It's not going to be a nice integer number. That's okay. Fractions are numbers too. That's your y-intercept. Yeah. Good job. Right now, burn up your battery. So you can darken if I set the second up arrow light by the second down arrow. So burn your battery go off. So you want 3 to be 0 minus 2. Basically 3 to the negative 2 power. Wow. 250 calories, but there's 2 servings per container. Like you're going to stop at 1 cookie.
Right. Let her live.
Sorry. How are we doing over here?
I'm tired. It's been a long day. So they always forget to put the 0.
Always forget what?
The 0 in the y-intercept.
Always putting in 0. Okay, so well, let's see. 3 to the x minus 2. How's that going to shift the graph? In which direction? Right by 2. So right by 2. Now, if it shifts it right by 2, that's not going to change the horizontal asymptote. If I take this graph and I shift it to the right 2, it's still the graph of y equals 0. So you're not changing the horizontal asymptote. As far as the y-intercept is concerned, you're always going to set it x equals 0 to get the y-intercept. That gives me 3 to the negative 2 power. But I'm hoping that you write 3 to the negative 2 as what fraction? 1/9. Good. So 0 and 1/9 should be your y-intercept there. How about down here? What's the minus 2 going to do in this case? Down 2. What's that do to your horizontal asymptote? Shifts it down 2. So was it 0? Now it's going to be down at 2. Negative 2. So y equals negative 2. If I set x equal to 0, 3 to the 0 is 1. 1 minus 2 is what? Negative 1. 3 down, 1 to go. So far, so good on these? Okay, let's keep going. Last one here. What's the plus 3 going to shift it as? Left 3. Does that change the horizontal asymptote at all? No, because if I shift this to the left by 3, it's still y equals 0. But I can find the new y-intercept. 0 for x gives you 2 to the third. 2 to the third is 8. 0 plus 3, 2 to the third is 8. So, yay. Now, Newton seems to be a little bit nicer to you than I'll be. Sorry. Let me give you another one like this in terms of shifting and see what we can do with it. I'd probably give you something more like this. So here's your f of x is 2 to the x again. Let's look at g of x equals 2 to the x minus 4 minus 2. So I'm throwing a lot of shifts at you. All right. All right, at least somebody got it. That's good. So what's happening here? There's really 2 shifts, right? So you got to take account of both of them. Start by figuring out where does this point go. That's key. You want to get that point correct. You also want to get the horizontal asymptote correct. The horizontal asymptote for 2 to the x is right here. It's along the x-axis. But that's going to get shifted because this graph has a vertical shift. So try and shift that. Draw in the new horizontal asymptote. Figure out exactly where this point goes. So let's take a look at this one. As far as the shifting is concerned, the -2 causes a shift of what? Down 2. So down 2. And then the -4 here causes a shift in what direction? Right by 4. So to the right by 4, 1, 2, 3, 4, and down. Really? All right. So and down 2, 1, 2. So that point is here. Please graph that point accurately. That point now has coordinates of 4, -1. That's the new point there. As far as the horizontal asymptote, the horizontal asymptote got shifted down by 2. So let's draw a new horizontal asymptote right here. This is a good guide to help you draw your exponential function. The graph shouldn't quite touch there. In fact, as far as drawing is concerned, if you start out at the x-axis or the asymptote, go through that point, that's a good way to avoid touching it or going through there. How are we looking with that one? Doing okay? Georgie? Doing good there? Thank you, sir. All right. So, a lot of practice with shifting of graphs. There is one last thing that I need to mention about these graphs. That is, we've been working with values of the base that are greater than 1. So when you look back at your original handout on the front side of things, these conclusions are for the value of the base that's greater than 1. But you could be dealing with, or you could be asked to deal with, a value of the base that's between 0 and 1. So what's going to happen in that case? Well, let's find out. Now, if I had it to do it again, I'd put 0 is less than b is less than 1. Because you have to have a positive value for the base. That was one of the things we mentioned initially. But if your value of the base is between 0 and 1, like it is for this function, f of x equals 1/2 to the x, then that's going to change your graph. Instead of a nice increasing function, so over here this is an increasing function, what do you think I'm going to call this one? If this is increasing, what do you think this one's doing? Decreasing. And it's very easy to decide which one you're going to deal with. It's just going to depend on the value of the base. So if the value of the base is between 0 and 1, then it's going to be a decreasing function. If it's between 1 and infinity, it's going to be an increasing function. So let's go back to our handout, onto the next page. And it's going to ask us to identify which of the following exponential functions is increasing. Well, you just have to look at the size of the base here. The base in this case is 5.3. So is that going to be increasing or decreasing? Increasing. How about the next one? Decreasing. And I'll give you a second to do the last two, but I'm hoping those are pretty clear. All right, so for the last two, what's going to happen with this graph? Good, decreasing, and the last one is increasing. Well done, thank you. Nice, these are all examples of exponential functions. There's a lot of applications about exponential functions. So let me just share a few with you. We've seen some. Let's see a few more here. Let's see. We'll start here. Slideshow from current slide. So we saw this one. The dominoes example talks about compound interest. That's a nice thing, exponentially growing. This one might not be quite as nice. This is the national debt. That looks kind of like an exponential function to me. So over here, that's your problem because I'll be dead. All right. What else is going to be your problem? World population. All right. Well, yeah. This is another problem. And hopefully I'll be around for at least part of that. But yeah, that's another problem. Population growth tends to be exponential. Yes. Get your oceanfront property. It's going to get crowded by the time you retire. Carbon dioxide levels. What's the concern about carbon dioxide? It's a greenhouse gas, right? Climate change, global warming. All right, this is a big problem. Here's let me give you a term let me give you an application that maybe you wouldn't think of. Have you ever heard of the term viral video? What does the term viral video mean to you? It gets really, really popular quickly, right? So in my mind, what's happening is that the number of views takes off and grows exponentially. That to me is what a viral video is when the number of views grows exponentially. And you see it here with Gangnam Style, the first video to get 1 billion views. That's staggering. That's like 1/7 of the planet. Connectivity, internet connectivity, devices that connect to the internet, that's grown exponentially. There's something called Moore's Law, which in computing talks about processor speed, that basically processor speed doubles about every 9 months. And this is a phenomenon that's been going on since like the early 70s. So it's pretty cool, and it's pretty accurate. Here's a different look at that same kind of graph. This one looks linear until you look at the scale. The scale isn't 1,000, 2,000, it's 1,000, 10,000. This is what's called a logarithmic scale, and we'll deal with logarithms soon enough. Then there's the flip side of this, when you have decay. So a decreasing function. You'll see that with radioactive decay. This is how they date lots of old things. Radiocarbon dating, potassium-argon dating, that kind of stuff. So tons of applications, more than we're going to cover here. Memory loss, Newton's law of cooling, lots of good applications for exponential functions. You see them all over the place. But the one that we're going to work on now is what, according to Einstein, is one of the world's most powerful forces. So it's a quote from Einstein. One of the world's most powerful forces. Anyone want to fill in the answer? No. Compound interest. Compound interest. That was literally a quote from Einstein. So the formula for compound interest looks like this. A equals P times 1 plus R over N to the NT. I will give you the formulas here. You don't have to memorize this. Yay! See? All right, yay. Give some love to the instructor. That's good. Let's practice how to use it. Suppose you're looking ahead at your education, you realize you're not going to be at OCC together or forever where it's nice and cheap. You're going to go on to a 4-year university, and then things are going to get really expensive. So you're like, okay, I'm going to put away some money. So what the money, well, that's your principal. Let's suppose you're going to put in $5,000. Okay, that's the principal. Rate of interest, right now you'd probably be lucky to get 2.5%. But there's something special that has to happen when you use these formulas. The rate of interest has to be expressed as a decimal. If it's not, then really you're giving yourself a lot more interest than you expect. So what's 2.5% as a decimal? I heard a couple things, but I didn't. You move this 2 places to the left. So 0.025. Make sure you don't put in 0.25. That would be 25%. You guys not have that one? Really? You don't have the equation? All right. Just in a different spot? My bad. All right, but all we need is the equation. We're going to run through how to work it So let's put in a couple more of these parameters. One of the things we need to figure out is how long it's going to be until you leave OCC. So let's say it's going to be 3 years before you need that money. And last but not least, how often is that money going to get interest? That's n. That's how many times a year interest is compounded. So let's say that n is 4. Okay. So now what? Now let's plug it all into this formula. And earlier I told you needed a graphing calculator. Here's where it's going to pay off. It's going to be 5,000 times parenthesis 1 plus 0.025 divided by 4 raised to the n times t. So it's going to be 4 times 3. If you've got an old TI-83, you might just want to do 4 times 3 is 12 and be kind of done with that part. Yes, we're going to put it all in at once, and let's practice that. So here's the way it's going to look. 5,000, parenthesis. You do not need to hit the times key. Your calculator understands that there's a times key built in. 1 plus 0.025 divided by 4, then a right parenthesis, raised. Now, if you don't feel like using your head a little bit, you can do 4 times 3. Or if you have an old TI-83, I'd suggest that what you do here is that in the exponent, you do the multiplication first and just raise it to the 12th power. Either way, you should get 5,388.16. I'm not sure why it's freaking out on me there. So 5,388.16. Now, why did I stop it here? Yeah. If you're talking about dollars and cents, that's where cents stops. That's where our units of currency stop, is the penny. So you're going to round your answers with interest down to the nearest penny. All right. If you didn't quite get that, let me help you out. Raise your hand. I'll come around and see if I can't figure out what you did wrong. So all right, so what you need most from the top of this sheet here is this formula that I have circled here, and then this part right down here where I do the calculation. This other stuff here I'm going to talk about in a minute. So, does anyone need help with getting that number off their calculator? All right, good on you guys. That's good. Now, what we're going to do next is kind of work with a fictitious example. Let me go back to my formula here, which is, let's see, A equals P times 1 plus R over N to the N times T. And work with kind of a fictitious example. An old favorite movie of mine is a movie called Trading Places. And in Trading Places, they had a standard bet. Does anyone remember what the standard bet was? It was $1. So that was their standard bet. Now, because this is a fictitious example, I'm also going to give you another fictitious number. We're going to give ourselves 100% interest on that $1. Woohoo! Yeah. Extra credit if you can find me an investment that I can get 100% interest.
How much extra credit?
Lots. As long as I can invest a lot of money in that, then yes. Now, the important thing is you need to rewrite that as a percentage, or I mean, as a decimal. So what's 100% as a decimal? 1. Exactly 1. Good. Now, good things aren't going to last forever like that, so our investment is going to go for 1 year. That's it. We did it 1 year. And if you take a look at this formula, everything has been set to 1 except one thing, n. So what's left is 1 times this. I'm not going to write the 1 out in front. It's just going to be 1 plus 1 over n to the nth power. What this is going to show you is the power of compounding interest. Remember I said earlier, Einstein said that compound interest is one of the most powerful forces in the universe. Let's see that. So we'll make a little chart here. N equals something. What's the amount of money we get back from our dollar investment? So suppose that n equals 1. Okay. Well, if n equals 1, you put in a 1 here. You get 1 plus 1 to the 1 power, or 2. And that makes sense. You get interest compounded once a year. You get 100% of a dollar. That's $1. They add it to your account. You've got $2. What about when n equals 2? Okay. You start out January 1. You've got $1. Halfway through the year, you get half of the interest. What's 50% of a dollar? 50 cents. Add that to your account, you got $1.50. At the end of the year, you get the other 50%. So what's 50% of $1.50? 75 cents plus $1.50 is now $2.25. Oh, okay. So that's kind of nice, right? We got an extra quarter because our interest was compounded. We got interest on our interest. So this is kind of a fun game. You're like, all right, well, hey, let's bump it up and do it quarterly. Now, I'm not going to try and work through the numbers with you. This is something you can put into your calculator. But if you compound interest quarterly, you're going to get $2.44 back. So that's kind of nice. Do some more. Well, another common interest would be to compound things monthly, 12 times a year. Now you're going to get back $2.61. Hey, I like this. So where could I go from there? I've gone from quarterly to monthly. The next stop would be daily interest. Now, how many days are there in a year? 365. But when bankers calculate your compounded interest, they're going to use 360. This is just the acceptance standard. They give themselves 5 holidays. It makes the most minimal difference to you, but in this case, we're going to get $2.71. So then you get a little impatient. You're like, okay, how about if we do hourly? So 24 times 365 is going to be 8,760. But look what happens to our interest. 2.718. Wow, it really didn't give us a lot extra, right? We didn't even get an extra half of a penny. Mathematically, in calculus, we can put in infinity. And what that means is you're compounding interest continuously. You never stop. Every second of every minute of every hour of the day of the year. You're always compounding interest. And what are you going to get then? You're going to get this magic number called E, which is 2.71828, etc., 1828, blah, blah, blah. And that goes on forever. Now, this is not a number you have to memorize, but what I'd like you to do is I'd like you to find it on your calculator. And I'll give you 2 places you can find it. So the first one on your graphic calculator is right above the division key. And you'll see it there. That's E. So E is the natural number. Other than pi, it's the most famous constant that there is. So hit the second key, then the division key, and you should be able to get E. If you've got a scientific calculator, then you can do something else. Or if you've got a graphing calculator, you can also do something else. You should also see E above the ln key. How do I get to this one? Second ln. This time it puts an exponent up there for you. If I want e to the first power, then it just type in a 1. Or I can do e to the second power, type in a 2. I can do e to any power that I want. So that's kind of nice. You've got this number which is the base of an exponential function. So that number e is really important and very handy, and it's also handy in calculating continuously compounded interest. Continuously compounded interest formula. And kind of like your other formula for interest, I would give this to you on an exam if I expected you to use it. A equals P e to the RT. That's for continuously compounded interest. If you look at interest that is compounded, periodically, n times a year, you'll see that this one has an n in it. That's because you have to have interest compounded every so often, and that's the value for n. When interest is compounded continuously, then there is no n. It's just built in. It's built in the form of e. So let's go back and take a look at our previous example. We had 5,000, 1 plus 0.025 over 4 to the 4 times 3 power. So when we were investing for college after OCC, we ended up with 5388.16. What if instead of getting interest compounded, 4 times a year, what if we could get interest compounded continuously? So we're going to take that $5,000 and invest it at 2.5% interest, which is 0.025 for 3 years. How much money am I going to get now from my interest formula? Am I going to get a lot more money? Let's find out. 5,000 second ln. That gives me something in the exponent. So I want 0.025 times 3. Now, if you got an older TI-80 something, what you should do is this. And let me just change my mode to kind of demonstrate that. If you got an older calculator, you do this 5,000 e to the parenthesis 0.025 times 3. But you need to have parentheses around that exponent if it's showing you something like this. And you should still get the same kind of thing. So about 53.89. And how many cents? 42. Do we make a lot more money by compounding continuously? No, not really. If this were to stay invested for longer, the results I think would be much more dramatic. But right now, let's just say that I hope you're not driving very far because you're going to spend more on gas than you're going to get in extra interest to put your money here. So the point, though, of course, is to get comfortable with our e to the x key, and that was the point there. Good with that part? All right. Wow. We're overdue for a break. There's a little bit more here. Do you want this in the same video? Yeah, all right. I appreciate you guys being tough about that. All right. It's not that much left. It's just, well, I'll finish it up quick. You guys got this graph on one of your handouts? Yeah. Okay, good. These will be the last two. So let me set this to E. Oops. E. And let's shut this off, this off. So this is the graph of e to the x. And on our handout, we're asked to graph a couple other things. E to the x minus 3. how is this graph going to be shifted compared to the graph of e to the x, which is actually already drawn for you? Yeah, it's going to be shifted down by 3. So let's just kind of roughly sketch in a couple things here. Down by 3 would be 1, 2, 3. So down here, 0, negative 2. And then way down here, yeah, you kind of fake it a little bit. At y equal negative 3, there's going to be your horizontal asymptote. And basically, it's the same kind of shape that we had right here, just shifted down. So that's your graph of y equals e to the x minus 3. So nothing much different. Just shifting that graph down. Over here. Yes. That's okay.
So like, if like a line, if it's like curved to the right a little bit, and accept still.
Look, as long as you've got it, you're going to have an example graph right here to model it. So you should be able to kind of mimic it reasonably. I mean, I'm not going to be overly picky, but I think I've mentioned the things that I'm concerned about. This should get close to this line. It shouldn't touch it. Don't go through it. Don't ricochet off of it. Those are the things I'd be looking for. I want to see where this point is. Take this one, shift it down 3. I want to see that one. So those are the important things for me as far as this graph is concerned. It should have the basic shape here, and all you have to do is kind of copy this shape right here, which is already given to you. Yes? Yes. Yeah. It's going to be like that. So let's take a look at this one. Try and figure out how this one's been shifted. So in your mind, figure out how it's been shifted, and then compare notes with your neighbor. Ask your neighbor how it's been shifted. See if you guys are on the same page. All right, talk it up a little bit. I don't hear anyone saying, oh, up, down, left, or right. Make some friends. Lexi, make a friend. August. How's it been shifted? Did it match yours? Okay, good. Yeah, where is he? Patrick, did you get a chance to compare answers? Okay, all right. Well, let's take a look at it together then. What's the minus 1 going to do as far as the shift is concerned? Right by 1. And then what? Up 2. Good. So let's see if we can't figure out what that does for their graph. Right by 1 is over here. Up by 2. Yeah, somewhere around here. Okay, looks good. What else should I change? The asymptote, right? So instead of a line here at y equals 0, where's the new asymptote going to be at? Good. So No, the yellow line is not the new one, which is good news. And then it's just a matter of drawing a nice increasing function through this point. So something like that. That works pretty good. Oops. Okay. How are we looking on that one? Good. Michelle? All right. Thank you. Thank you. Whew! I think we deserve a break. Give yourself a round of applause. Yay!